Hello everyone, this is the third lecture regarding the chapter 3. Since we already get the main hashing to compress large document into small signatures, which still preserve the expected similarity of any pair of documents, as illustrated in the last videos. It may still be impossible to find the pairs with the greatest similarity efficiently. The reason is that the number of pairs of documents may be too large, even if there are not too many documents. If our goal is to compute the similarity of every pair, there is nothing we can do to reduce the work, although parallelism can reduce the elapsed time. However, often we want not only the most similar pairs, or all pairs that are above some lower bound in similarities. If so, then we need to focus our attention only on pairs that are likely to be similar without investigating every pair. So there is a general theory of how to provide such focus called locality sensitive hashing, like LSH or near neighbor search. So in this lecture, we'll consider a specific form of LSH designed for the particular problem we have been studying regarding the documents represented as single sets, then min hashed to short signatures. Now it's a first cut regarding the LSH. The goal, as we mentioned before, is to find the document with J-card similarity, at least S as the similarity threshold. The LSH general idea is that using a function which tells whether X and Y is a candidate pair, a pair of elements whose similarity must be evaluated against above or below the threshold. As for the min hash matrices, hash columns of signature matrix M to many buckets, and also each pair of documents that hashed into the same buckets is called candidate pairs. So the general approach to LSH is to hash items several times in such a way that similar items are more likely to be hashed to the same bucket. Than these similar items are. We then consider any pair that hashed to the same bucket for any of the hashings to be candidate pairs. We will check not only the candidate pairs for similarity. We hope that most of the dissimilar pairs will never be hashed to the same bucket, and therefore will never be checked so as to reduce the computation cost. And all those dissimilar pairs that do hash to the same buckets are called false positives. We hope this will be only a small fraction of all pairs. We also hope that most of the truly similar pairs will hash to the same bucket under at least one of the hash functions, like those do not called false negatives. We hope this will be also only a small fraction of the truly similar pairs. If we have main hash signatures for items, an effective way to choose the hashing is to divide the signature matrix into B bands consisting of R rows. Before dividing, first we need to set up a similarity threshold. The threshold is used to measure the columns belong to the same matrix, like candidate pairs. If their signatures agree on at least a fraction S above the threshold, then the XY will be the at least the fraction S values of I. We would expect the documents X and Y have the same J-card similarity as their signatures. Using the LSH to mean hashing, the big idea is, like I said, we are trying to hash the columns signature or matrix several times, and before we really put into the similar columns to be hashed into the same bucket with high probabilities, and all the we expect that the candidate pairs are those that can hash to the same bucket as well. Like I said before, in order to reduce the computation cost, we need to partition the matrix into B bands, and each band will consist of R rows, and this is the portion of one column within that band as well, and so that we can hash them into the same large number of buckets. We can use the same hash function for all the bands, and we use the correct bucket array for each band, so the columns with the same band can be put into the same bucket as well. Okay. So this slide is concrete steps how to operate in the partitioning operation of our matrix into bands as well. When we hashing the bands into different buckets, this figure illustrates that, for example, if for any band, for example, we got different columns here, since the column 2 and the column 6, they are probably identical, so that they can be mapped into the same bucket. The similar situation happens with the column 1 and the column 5. They are put into the same bucket because of the potential identity. Okay, but in the 6 and the 7, they are surely different, so they are being put into different bucket in the identical in the similarity evaluations. There is an assumption regarding the simplification. Suppose we have enough buckets that the columns are unlikely to hash the same bucket unless they are identical in a particular band, which means that we have enough buckets to hold all the differences bands. So thereafter, we assume that the same bucket means identical in that band. So this assumption is needed only to simplify analysis, not for the correctness of the algorithm. As we know that the correctness it should be evaluated with another different algorithms and parameters. Here is an example of bands. Assume that we have the following case. Suppose we have 100,000 columns of matrix to present 100,000 documents. Okay, so the signatures is about 100 integers, which is composed with 100 rows, which means that each document has 100 rows. Therefore, we will probably have the signatures taken about 40 megabytes. If we choose B to present 20 binds and R equals to 5 integers per band to present each band. Okay, so the target is that we are trying to find any pairs of documents that have at least about 80% in similarities. So how can we execute this task? Seeing that suppose we have C1 and C2, we are trying to find out the C1 and C2, they are at least 80% in similarities. Okay. Since we need the similarity of C1 and C2 beyond the S, we need the C1 and C2 to be a candidate pair, so that we want them to be hashed at least one common bucket, so that they have to be hashed in at least one common bucket for the similarity to present that at least one band is identical. The probability that C1 and C2 are identical in one particular band is can be presented about 0.8 with power 5, since it has 5 rows for each band. 5 rows for each band. So each rows are independent. So the final result will be the power of 5. And so that they are totally identical in five rows is can be calculated like 0.328. So the probability of C1 and C2 are not similar in all the 20 bands is another also independent events, which can be calculated with 1 minus 0.328 with the power 20. With the power 20, because this similarity is compared across all the 20 bands. So the results will present with 0.00035. So that's about 1/3000th of the 80% similar columns are false negatives, so which can be easily ignored, so that we can find at least 99.965% pairs are truly similar documents. So how can we find other columns or documents if they are about 30% similar? Suppose we already have the similarity threshold about 0.8. We still get the band number of 20, and each band we got are 5 rows. So we assume the similarity is 0.3. Since the similarity is below the threshold, we want the column C and column 2 to hash to no common bucket, which means that they should be appear in different bucket. The probability that C1 and C2 identical in one particular band is that they are 0.3 with power 5, so we got 0.00243. The probability of C1 and C2 are identical in at least 1 of 20 bands. So this will produce the equation if you we got from the statistics that 1 minus also with the 1 minus 0.234 with the power 20 also minus equals to 0.0474. In other words, approximately 4.7% pairs of documents with similarity of 0.3% end up becoming candidate pairs. So all these candidate pairs are false positives, which should be examined when we turn out their similarity is below the threshold. So this is two examples how we calculate the C1 and the C2 in the similarities. Well, the local sensitive hashing practically involves trade-off features. If we still pick the number of main hashing rows of M, and we still got the number of bands like B, and each band got R rows, how can we balance the false positive and negatives? Okay, so let's take an example to illustrate such implementations. If we had only 15 bands of 5 rows, the number of false positives would go down, but the number of false negatives would go up. The reason is based on this analysis of local sensitivity hashing. Like we noticed from this figure, the similarity is more like a threshold function, which give a high step upswing when it is above the similarity threshold. Okay. Shall we start from the simplest instances? What about if a matrix have only one band and a one band and a one row? So we get these linear functions in this figure. The probability of sharing a bucket is can be linearly increment with this similarity of any two sides of column 1 and column 2. Suppose we still get the B bands and R rows per band. The columns C1 and C2, they have the similarity like T. The T will probably be calculated based on the different parameters. Say we pick up any band composed with R rows, so the probability of all rows in the band are equal, totally identical, can be computed like T with power R. since each rows are independent variables in the random process. In the meanwhile, that if we calculate if there are some rows in band are unequal, which means equals to the 1 minus t with the power r. So this is very easily to be analyzed from the statistics and stochastic analysis. Well, the probability is that no band are identical at all can be represented with 1 minus t with power r, and also powered with a b in the outer square. Okay, so the probability that at least one band identical is also 1 minus the probability that no band is identical at all. So these are all the statistics formulations regarding the B band. Based on this all these formulations, we can put all these numbers into this figure to present their meanings and the efficient and the effective in the figures. Okay, so with the B band and R rows, if we put into this figure, we will notice that the similarity is actually kind of proportional to 1 divided by B, also with the power of 1 divided by R. So about at least one band are identical and no band are identical, and some rows of the band are identical. All rows of this band are identical. We can extract it from this formulation to understand each meaning respectively. Okay, like I repeated that t power with r represent all rows of a band are identical, and also as a union, at least they have some rows are identical, is 1 minus with t power with r. And so since based on this one, we can exact that at least one bands, no bands are identical at all is power with b, and at least one band identical is 1 minus with these parameters. So this is a function shape, a curve in the graph. So if we put into the calculations here, we will notice that if we got the similarity threshold, we like a 0.2, we will notice that the probability that at least one band is identical can be calculated based on this table here. So we got, if we have the threshold of the 0.8, we have the possibility of 0.9996 to of that at least one band is identical between the columns of C1 and C2. Okay, so the next question is that how can we pick up the right and the efficient R and B to shape the proper S curves. As we mentioned before, we have the 50 hash functions. If we are taking the R equals to 5 and B equals to 10, which means that we divide the matrix into 10 bands, and each band will include 5 rows. The curve can can be illustrated in this image, and we will notice the blue area present the false negative rate, and the green area present the false positive rate, which means that we should be put into positive, which has been identified as negative, while the green area the should be the negative, identified as negative, but actually was identified as positive. So now we can have an approach to find the set of candidate pairs of similar documents, and then discovering the true similar documents among these curves. It must be emphasized that this approach can produce, as I said, false negatives, pairs of similar documents that are not identified as match, because they never become a candidate pair. There will also be a false negative, which means the candidate pairs that are evaluated but are found not to be sufficiently similar. So the implementation details we should include the following steps. The first, we need to pick up a value of k and construct it for each document, like a set of k shingles. Okay, and in the second step, we need to sort the document single pairs to order them by shingles. In step 3, we need to pick length n for the mini hashing signature to produce the min hashing signatures to feed the sorted list to the algorithm to compute the min hash signatures for all of the document. In step 4, we need to choose a threshold S that to define how similarity of documents can be put into order for them to be regarded as the desired similar pairs. In step 5, we also need to construct candidate pairs by applying the local sensitive hashing techniques. And in step 6, we need to examine each candidate pair's signatures and determine whether the fraction of the component in which they agree with at least threshold S. With another option, if the signatures are sufficiently similar, we need to go to the document themselves and to check whether they are truly similar rather than document just similar by luck. Probably they just occasionally have similar signatures. So as a summary of local sensitive hashing, the parameters of matrix M are bind and R to get almost all pairs with similar signatures, but we need to eliminate most pairs that do not have similar signatures. Okay, so we should always check in the memory that candidate pairs really do if they have similar signatures. As another optional path with the data, we need to check the remaining candidate pairs whether they really represent similar documents. So like a small conclusion regarding the 3 steps about the local sensitive hashing. The first step is shingling, which turns the documents into string sets. Here we use the hashing function to assign each shingle an ID. In the second step, the min hashing was implemented to convert large string sets to short signatures, which has been presented in the previous slides. This transformation and conversion still preserves the similarity between different columns of different documents. As we had already proved the similarity preserving hashing to generate the signatures due to the property of the probability of the permutation of C1 and C2 equals to the similarity of the C1 and C2. So with this property we can hash the different columns around to generate random permutations. In the third step, the locality sensitive hashing are used to find the near neighbor items to focusing on the pairs of signatures likely to be from similar documents. Especially we need to set up a threshold as to measure whether the candidate pairs are beyond the similarity threshold. Okay, this is a small conclusion about the LSH. As to the important content in the chapter 3, we have a very quick reminder. In the first, we started to introduce the J-card similarity to present the ratio of the size of the intersection of the sets to the size of the union. This is this measure of similarity is suitable for many applications, also including textual similarity of documents and the similarity of buying habits of customers. Okay, and the following three steps, which we have mentioned, is like shingling to present. To convert the document into a K shingle sets, and main hashing to present the hashing result and with the permutation of the universal sets. And a very important concept is the main hash signature, used to present the list of the permutation and computing and also used to computing each side of its main hash signatures, which is also the sequence of main hash value to be obtained by applying each permutation on the list of that set as well. The next concept is the efficient main hashing, which is used to which is not really possible to generate random permutation, but it's normally to stimulate permutation by picking a random hash function, like taking the main hash value for the set and to be at least a hash value of any of these set numbers. The following concept is locality sensitive hashing for signatures. This technique allows us to avoid computing the similarity of every pair of sets or their main hash signatures. If we are given signatures for the set, we may divide these signatures into bands, and each band contains several rows. So we need to choose the proper size of the bands and the rows so as to eliminate from the consideration of most of pairs that shouldn't be taken as false positive and false negative. And there is also another very important section in chapter 3 is regarding the distance measures. These measures has been discussed across many different measurements, and including the Euclidean distance, J-car distance, cosine distance, Edith distance, Hamming distance, and which I believe is already being familiar with many of you to learn from the in other courses. I think that's all for the chapter 3, which is composed with 3 individual videos. Okay, so I do hope you understand the LSH and get most out of the lectures here. Okay, thank you everybody.